Greetings of the day to all of you. Today we are going to start a new topic in our course on pulse width modulation techniques. The topic of discussion today is over-modulation. I will write here over-modulation of voltage source inverters. First of all, the question is, why do we study this over-modulation? Do we really require over-modulation? See, the answer to this question is that if you don't over-modulate your PWM voltage source inverter, then you will not have better utilization of DC bus. For example, if DC bus voltage is, say, or DC link voltage is 600 volts, we want to, out of what we are doing through this PWM voltage source inverter, we are converting this DC voltage into AC voltage. And RMS value of fundamental component of AC voltage should be as high as possible as far as this DC bus or DC link voltage is concerned. And you have seen in single phase PWM voltage source inverters as well as in three phase PWM voltage source inverters, even if modulation index is equal to unity, the inverter output voltage is not as high as that for a square wave mode of operation. You remember when we operate a single phase PWM voltage source inverter in square wave mode like this, the voltage waveform is like this. This is the output voltage waveform of a single phase single phase voltage source inverter operating in square wave mode of operation. And if you take fundamental component of the voltage, see this is 0, pi, 2 pi, the peak value of fundamental component of voltage, let's call that V01. And if you remember, we have already derived an expression while discussing square wave voltage source inverters. The peak value of fundamental component of inverter output voltage for square wave mode of operation is 4 pi pi VDC, which is roughly 1.273 VDC. Okay, so therefore, if you are VDC, that is DC link voltage, is say 400 volts. It's DC, okay? Your peak value of fundamental component of inverter output voltage will be 1.273 times 400 volts. So that means this is the maximum voltage that you are able to, get from an inverter, okay? Then you can find RMS value of fundamental component of inverter output voltage, that is peak value by under root 2. The RMS value is peak value by under root 2, that is 1.273 into 400 by under root 2. So you can compute this. This is the maximum voltage which you can get from an inverter. But the problem is that when you get this maximum voltage only when you operate your inverter in non-PWM mode or in square wave mode of operation. Same is the case with three-phase PWM voltage source inverters. In three-phase voltage source inverter, when you are going for square wave mode of operation, your phase voltage is something like this. It's a 6-step voltage. This is say for phase voltage VRN. Similarly, you have other two phase voltages VYN and VBN, which are 120 degrees phase displaced with respect to each other. And if you draw the waveform for line voltage, say one line voltage VRY, it's something like this. It's not exactly square, it is quasi-square wave. And then you can, find the fundamental component of voltage, and the peak value of fundamental component of voltage is maximum in this case. So the conclusion is that there will be best utilization of DC bus voltage, which means that maximum from the given DC bus voltage, we can have maximum inverter output voltage only when we operate the inverter in non-PWM mode or in square wave mode of operation. But we never go for square wave mode of operation because of the harmonic distortion of the voltage. This voltage as well as these voltages, they are very rich in harmonics. For example, if you consider single phase voltage source inverter in square wave mode of operation, it will have all lower order harmonics, triplen as well as non-triplen harmonics. That means this voltage waveform will comprise of, in addition to fundamental component, it will have very strong third harmonic component, a very strong fifth harmonic component, then followed by 7th, 9th, 11th, 13th, 15th, 17th, and so on. and it will be very difficult to remove those harmonics. And this voltage, this voltage waveform, which has high level of distortion, is unacceptable for most of the applications, especially in those applications where voltage sensitive loads have to be operated, like induction motor drives, medical equipment, microprocessor based control, and all that. Same is the case with three-phase voltage source inverters. When you are operating a three-phase voltage source inverter in square wave mode of operation or in 6-step mode of operation, you get no doubt maximum fundamental output voltage. That means you get the best utilization of DC bus voltage. From a given DC bus voltage, you are able to extract or produce maximum AC output voltage, but at what cost? At the cost of very high distortion in the inverter output voltage, which again I would like to say is unacceptable in most of the applications. So that is why we go for pulse width modulation control. That is one reason, because we want to get rid of these notorious lower order harmonics. And secondly, if you operate in your voltage source inverters in 6-step mode or in square wave mode of operation, it's not possible to control the magnitude of inverter output voltage. Fundamental component of inverter output voltage is fixed. We cannot control it. So therefore, for two reasons, we go for pulse width modulation. Number one, we want to get rid of lower order harmonics, which are very difficult to filter out. And when we go for pulse width modulation, when we apply PWM technique in any inverter, whether it's a single phase voltage source inverter or three-phase voltage source inverter, the harmonic spectrum shows that there are no lower order harmonics. There are harmonics around carrier frequency, multiples of carrier frequency, and their sidebands, which are very, very minuscule or which are very weak in amplitude, and they are very easy to filter out. Okay, if your load is an induction motor, then induction motor winding reactance itself is sufficient to filter out harmonics in the current because of this PWM operation, and thus produce almost purely sinusoidal winding currents in induction motor, right? And secondly, by changing the modulation index of the inverter, we are able to control the fundamental component of inverter output voltage, which is one of the requirements of most of the inverters. Okay. Now, the problem with PWM operation of inverters is that, even if the modulation index M is equal to 1.0, which is the maximum modulation, the inverter output voltage is not maximum, okay? Because there will be still, notches, because inverter output voltage is like this. So for example, you may get inverter output voltages like this. Near the peak, there may be some sort of, some pulse dropping. This is in one half cycle. Similarly, in other half cycle also, you will get something like this. So in the middle, if modulation index is 1, modulation index 1 means, for example, if this is your modulating wave, say MR, and this is your carrier wave, say modulating wave, you make its amplitude equal to 1. Your carrier wave is also 1. So if you make modulation, amplitude of modulating wave equal to carrier wave, that is MR is equal to 1, which is same as amplitude of triangular carrier wave, which is also 1. Then at that time we say modulation index is 1.0. Even if modulation index is 1.0, because of notches in the inverter output voltage, this inverter output voltage PWM, switched voltage pulses, because of these notches, the inverter output voltage, if you compute the fundamental component of inverter output voltage V01, it will not be as high as that for square wave mode of operation, because in square wave mode of operation you don't have any notches. You have a continuous pulse like this in the positive half cycle, and you have a continuous pulse in the negative half cycle like this. You don't have these notches. Because of these notches, the inverter output voltage is less in PWM operation than in square wave mode of operation, even for highest value of modulation index, which is unity. Okay, if you remember in when we were discussing single phase PWM voltage source inverters, we had got, I will write here, for single phase PWM voltage source inverters, the peak value of fundamental component of inverter output voltage, if you remember, that was given by this expression, that was given by MA into VDC, MA into VDC, where MA is the modulation index. Okay, and for modulation index equal to 1, what is inverter fundamental component of, what is peak peak value of fundamental component of inverter output voltage for MA equal to 1? It is VDC. Whereas for square wave mode of operation, what is peak value of fundamental component of inverter output voltage? That is 4 by pi VDC, which is 1.273 VDC. That means square wave operation gives about 12.73% higher voltage. I mean, it gives much higher voltage than pulse width PWM mode of operation. For modulation index equal to 1, the maximum value of maximum peak value of inverter fundamental component of inverter output voltage is only VDC, whereas for square wave mode of operation it is 4 by pi VDC. Okay, now that means in PWM operation, when you are using PWM voltage source inverters, there is not better utilization of DC bus voltage. Okay, if your DC bus voltage is say 400 volts, the inverter peak value of fundamental component of inverter output voltage for unity modulation index is same VDC 400 volts, whereas for square wave mode of operation it is 1.273 times 400 volts. It's higher in this case. So that means DC bus is not properly utilized in PWM operation than in square wave mode of operation. There are certain applications like induction motor drives where we would like to utilize the DC bus voltage, because you cannot have very large DC bus voltage. So you may have a DC bus voltage or DC link voltage of, for example, 600 volts DC, of course, and from this you want maximum inverter output voltage. So that means you want a better utilization of the DC output voltage, so that this V01 is V01 max, it's max. But PWM operation does not produce that. So that is why what we do is that we go for over-modulation. In over-modulation, what we do, the peak value of modulating wave, we make higher than the peak value of high frequency triangular carrier wave. And that gives rise to what we call as over-modulation. The question is over-modulation only solution? The answer to this question is no, over-modulation is not the only solution. In bus clamping PWM techniques also, we get higher voltage. For example, bus clamping PWM techniques. We have studied various types of bus clamping PWM techniques or discontinuous PWM techniques, like your continual clamp PWM technique, split clamp PWM technique, 60-degree clamp PWM technique, 30-degree clamp PWM technique. There we have seen that each phase leg is clamped to DC bus for 120 degrees in a line cycle. That means in one cycle. Okay, so that means when a particular phase leg, say there is switching and then phase leg is clamped to positive DC bus. This may be VRO pole voltage, and VY in the negative half cycle also it's clamped to negative DC bus. It's clamped to positive DC bus for 60 degrees in positive half cycle, and negative DC bus for 60 degrees. 60 plus 60 is 120. That means in one line cycle, total clamping period is 120 degrees, 60 plus 60. And during this bus clamping period, what is the inverter output voltage? I mean, what is the peak, what is the pole voltage? Pole voltage during this period is plus VDC by 2, and during this bus clamping period it is minus VDC by 2. There is no switching taking place during this entire period of this phase leg R. Similarly, in the negative half cycle, the phase leg R is clamped to negative DC bus, so that pole voltage is minus VDC by 2, no switching occurs. So this raises the inverter output voltage. There is pulse dropping during these periods. There are no notches, you can see. When notches are removed in the inverter output voltage, that means fundamental component of inverter output voltage increases, and we have already seen that all bus clamping PWM techniques or all discontinuous PWM techniques, they raise inverter output voltage by about 15.5%. So there is a rise in the inverter output voltage by about 15.5% as compared to sine triangle PWM. Same is the case with third harmonic injection PWM. Okay, if you consider third harmonic injection PWM technique, in third harmonic injection PWM technique for K equal to 1 by 6. The inverter output voltage, fundamental component of inverter output voltage, is raised by about 15.5% here also. Not for K equal to 1 by 4. For K equal to 1 by 4, it is raised by about 12%. For K equal to 1 by 6, in third harmonic injection PWM technique, the peak value of fundamental component of inverter output voltage is raised by about 15.5%. Okay, we have already studied this. Similarly, in conventional space vector PWM technique, in space vector PWM technique and space vector based bus clamping PWM techniques, bus clamping and advanced bus clamping PWM techniques, and advanced bus clamping, we have already studied these bus clamping and advanced bus clamping PWM techniques. They also give peak value. They also, all of these space vector based conventional space vector PWM technique and space vector based bus clamping PWM techniques and space vector based advanced bus clamping PWM techniques, they also raise the peak value of fundamental component of inverter output voltage. They also raise it by about 15.5%. Okay, so that means since if you consider in the continuous PWM technique, we have third harmonic injection PWM technique for K equal to 1 by 6, we can get 15.5% higher inverter output voltage. The same results we can get in conventional space vector PWM technique or space vector based bus clamping and advanced bus clamping PWM techniques. They also raise the inverter output voltage by about 15.5%. But still the DC bus remains underutilized. If you want more inverter output voltage, if you want to raise inverter output voltage more than 15.5%, then the only technique is to go for over-modulation. If you remember, so I will write here for best utilization of DC link or DC bus voltage, or for best utilization of DC link or DC bus, over-modulation is used in PWM voltage source inverters. We go for over-modulation. Okay, if you remember, for single phase PWM voltage source inverters, I had shown you a graph between modulation index and inverter output voltage. See, this is peak value of fundamental component of inverter output voltage normalized with respect to the DC link voltage or DC bus voltage. And you know, it was something, the graph was something like this. It was linear graph up to a modulation index of unity. And at modulation index of unity, the inverter output voltage was, we know that peak value of fundamental component of inverter output voltage is MA into VDC. For a modulation index of 1, MA is equal to 1, so it is VDC. And what is, this is for MA equal to 1, V01 is equal to VDC. So therefore, what is V01 by VDC? It is 1, so it is 1. Okay. And then if modulation index is greater than unity, that means we go for over modulation. So यहाँ से यहाँ तक आपका under modulation है. Okay, this is UM means under modulation. उसके बाद we go for over modulation. When we go for over modulation, inverter output voltage increases, but it increases in a non-linear fashion till we reach a very high value of modulation index. Say your modulation index may be roughly around say 3.24, and for modulation index of 3.24, your inverter goes into square wave mode of operation. And for square wave mode of operation, we already know that peak value of fundamental component of inverter output voltage is 4 by pi VDC. So what is this V01 by VDC? That is equal to 4 by pi. 4 by pi is 1.273. So this is 1.273. And so therefore, ये आपका over modulation zone है. No doubt this whole is PWM operation, PWM mode of operation. PWM mode of operation we have divided into two modes, under modulation mode and over modulation mode. You can see in the under modulation mode, as you increase the modulation index, your inverter output voltage increases linearly. So ये इसको आप कह सकते हैं linear mode. It is linear PWM mode. And when you go into over-modulation mode, your inverter output voltage increases with increase in modulation index, but it does not increase linearly. It increases in a non-linear manner. So this is non-linear operation, non-linear mode of operation. So your PWM mode is divided into linear mode of operation, which belongs to under modulation, and non-linear mode of operation, which belongs to over modulation. Okay, and as you can see, as you go from under modulation mode to over modulation mode, you are able to increase the inverter output voltage till you reach square wave mode of operation. यहाँ के बाद आपका square wave mode of operation है. After this, you have square wave mode of operation. This is PWM mode of operation, and then for a fairly high modulation index, say around 3.24, 3.25, your inverter degenerates into square wave mode of operation, and it gives maximum output voltage of 1.273 per unit. So this is square wave mode of operation. So therefore, this is your over model. This is how your inverter behaves in a non-linear fashion in over modulation mode of operation. But in over modulation mode of operation, you can see that inverter output voltage is higher than for unity for a modulation index of 1. You are able to increase the inverter output voltage for given DC bus voltage. So that means you are making more utilization or better utilization of your DC bus or DC link. Okay, but at what cost? When you go from under modulation mode to over modulation mode, no doubt you are utilizing the DC link in a better way. You are producing more and more higher and higher inverter output voltages, but at the cost of some harmonic distortion of the inverter. It produces a low frequency. There will be low frequency distortion in the inverter output voltage. Okay, so in the under modulation mode, there will be no low frequency harmonics, but as you go from under modulation to over modulation mode, some lower order harmonics will reappear in the inverter output voltage. So there will be some level of low frequency distortion in the inverter output voltage. But there is no alternative. For example, if you want to make best utilize of DC link, like in applications, say in induction motor drives, high power induction motor drives, we operate our induction motor drives in over modulation mode of operation for better utilization or best utilization of DC link and for producing higher inverter output voltages. Okay, so therefore we have to go for certain applications, we have to go for over modulation. Now let us discuss this over modulation for three-phase PWM voltage source inverters. So we will discuss this over modulation for three-phase PWM voltage source inverters. Okay, so first of all, we will discuss OM. OM means over modulation in the range. First of all, we will discuss over modulation in the range 1.0 less than M less than 1.15. We have a three-phase PWM voltage source inverter. We will discuss over modulation in this range. That is, the modulation index is greater than 1.0 but less than 1.15. This is the range. Because in different ranges, your inverter will behave differently. Let us try to study it in details. First of all, we will take the range of modulation index 1 to 1.15. That means your modulation index greater than 1 but less than 1.15. Let us take a specific value of modulation index. So we will take a modulation index of 1.1. Okay, that is greater than this. What is modulation? When does modulation start? I have already told you modulation starts when peak of a sinusoidal modulating signal exceeds carrier peak. Okay, so for example, something like this. Your carrier is like this. This is your carrier wave. It has a peak of 1.0 and negative peak of minus 1.0, and this may be your modulation index. This may be your sinusoidal modulating wave. You can call this MR for phasor. You can see the peak of modulating wave. It may be 1.1. I mean, you can see it is greater than peak of carrier wave. So therefore, your inverter is now operating in the over modulation mode of operation. Okay. So therefore, my three-phase modulating waves in the over modulation mode will be something like this. This is modulating, sinusoidal modulating wave or target reference wave MR. This is one, its peak value is 1.1. That means you are operating it in the over-modulation mode of operation. Negative peak is also 1.1. और ये आपका, this is your 1.0. This is the peak of carrier wave, minus 1.0. Okay, this is MR. So similarly, we'll have MY. This is modulating wave MY, and we have third sinusoidal modulating wave MB. This is MB. So these are our three sinusoidal modulating waves, MR, MY, and MB. They are compared with high frequency triangular carrier wave like this. We have high frequency triangular carrier wave like this, so on. You can see that triangular carrier wave has a peak value of 1 only, but the peak of modulating reference waves MR, MY, MB are slightly greater than this 1.1. So this is over-modulation, right? Now, because of this over-modulation, for example, in this period, यहाँ से यहाँ तक से आपकी, अगर आप फिर से carrier draw करेंगे, it's like this. From this instant to this instant, यहाँ से यहाँ तक आप देखेंगे, the peak of carrier wave is higher than the peak of modulating wave, but from this instant to this instant, the peak of modulating wave is greater than peak of carrier wave. So when peak of modulating wave is greater than peak of carrier wave, that means if you take inverter leg, say phase leg R, you take. This is inverter phase leg R. It is controlled by modulation, your modulating wave MR. So this is switch S1, this is S4. ये आपकी DC bus है. Total DC bus voltage is VDC, and this is VDC by 2. This is also VDC by 2. What is VRO? So for example, from this instant to this instant, there is switching of phase leg R. Whenever reference sine wave or modulating wave is greater in amplitude than triangular carrier wave, top switch S1 is on. And whenever triangular carrier wave is higher in amplitude than modulating wave, bottom switch S4 is on. So there is high frequency switching between S1 and S4. S1 is on, then S4, then S1 again, then S4 again, and so on. But from this instant to this instant, the peak of modulating wave MR is greater than peak of triangular carrier wave. So that means from this instant to this instant, the modulating wave is greater than carrier wave. So top switch will remain on. And when top switch will remain on, what will be VRO, pole voltage VRO? It will be plus VDC by 2, and there will be no switching from this instant to this instant. Because from this instant to this instant, the reference sine wave or modulating wave is higher in amplitude than triangular carrier wave, and top switch remains on during this entire interval, even if there are high frequency triangular carrier waves, but no switching occurs. S1 is on permanently, and VRO is equal to plus VDC by 2. Okay, so therefore there is dropping of the pulses. There are pulses from, pulses, you get the pole voltage pulses like this, plus VDC by 2, minus VDC by 2, plus VDC by 2, minus VDC by 2, and then there are no pulses during this period. Let me call this period X and this Y. From X to Y, there are no voltage pulses. Before X, there are voltage pulses. After Y, there are voltage pulses. Plus VDC by 2, minus VDC by 2, as far as pole voltage VRO is concerned. But from X to Y, there is bus clamping, or there is dropping of the pulses, because the top switch S1 is permanently on during this entire interval X to Y. And so there is pulse dropping here. Pulse dropping. And this pulse dropping results in clamping of your phase leg R to positive DC bus. And what is the maximum? What is the DC bus voltage? What is the pole voltage during this interval? It is VDC by 2. So therefore pulse dropping occurs. So because of this pulse dropping, if you find the instantaneous average value of pole voltage, instantaneous average value of pole voltage will be now something like this. Let us now draw three-phase average pole voltages. Average pole voltages. So we have three-phase pole voltages, VRO, VYO, and VBO. This is omega t axis. So for example, if over-modulation was not there, I have already told you that your pole voltages are scaled version of modulating waves. For example, your average pole voltage, VRO average, would have been M VDC by 2 into VP into MR. Okay, MR I have already written. So it would have been VDC by 2 VP into MR. So it is this is the gain of inverter. Your modulating wave is sinusoidal modulating wave. The instantaneous average pole voltage VRO would have been the scaled version of this MR. It is equal to MR multiplied by gain of the inverter. So that is if you are if there was no over modulation. Okay, for over modulation, your average pole voltage VRO would have been sinusoidal like this. It would have been a scaled version of modulating wave MR. Similarly, MY, VYO and VBO would also have been scaled version of their respective modulating waves. Like this. But what happens near the peak of each modulating wave? There is bus clamping, there is pulse dropping. I mean, यहाँ से यहाँ तक क्या होगा? Your pole voltage VRO, instantaneous average pole voltage VRO, will be same. I mean, it will be same as your modulating wave MR, sinusoidally varying like this. Okay. In fact, this what should I say? It would have been the scaled version of MR. But what happens from X to Y? The peak of modulating wave is greater than triangular carrier wave. So phase lag R gets clamped to positive DC bus और यहाँ से यहाँ तक. The inverter instantaneous average pole voltage is 0.5. Okay. Because what is the pole voltage VRO during this period? VRO average. This is VRO average. Pole voltage during bus clamping period when there is pulse dropping, it is plus VDC by 2. So it is 0.5. Its amplitude is 0.5. Then it again follows MR, and then there is again pulse dropping here. It is minus 0.5, minus 0.5. Then it goes like this. Okay, this is MR, VRO average, pole voltage VRO, VYO average, VYO average will be like this. Pulse dropping near the peak because of over modulation. This is your VYO average pole voltage VYO, and average pole voltage VBO, something like this. This is VBO average, right? So you can see during this instant, during this region, only phase lag R is clamped to positive DC bus, whereas phase lag Y and phase lag B, they are switching. In other words, during this period, only phase R has pulse dropping. When a particular phase lag is clamped to positive DC bus or negative DC bus, there are no pulses, there is pulse dropping. Whereas during this instant, what about phase lag Y? Phase lag Y is switching and phase lag B is also switching. So therefore we can say that the depth of over modulation is not very high. At any instant of time, you will see that there will be pulse dropping of only one particular phase. Say during this period, phase lag R की pulse dropping हो रही है. During this instant, only phase lag B has pulse dropping. During this instant, यहाँ से यहाँ तक, phase lag Y has pulse dropping. Then during this instant, phase lag R has again pulse dropping. So therefore, that means for a particular instant of time, only one phase lag will have pulse dropping due to over modulation. Okay. Other two, these phase lags will be switching. Okay. So other two phase lags are switching. This is in continuation with this, or switching. I'm considering this period. Only phase R has pulse dropping. Other two phase lags, that's phase lag Y and phase lag B, they are switching. So that means depth of over modulation is not high. Now we can very clearly see what happens to your pole voltage. In under modulation mode, up to a modulation index of 1, your pole voltage is having same waveform as your reference sine wave or modulating waves. Since your modulating waves MR, MY, MB are sinusoidal, pole voltages being scaled version of modulating waves, they were also sinusoidal. But as soon as you go into over modulation, you can see there is pulse dropping near the peak, near the positive peak, negative peak of each average pole voltage. So the average instantaneous pole voltages are not sinusoidal. There is low frequency distortion introduced into these pole voltages. Okay. What about line voltages? Three-phase average line voltages. Three-phase average line voltages will look like this. They will also have now low frequency distortion in them. This is 1.0 and this is minus 1.0. This is line voltage VRY average instantaneous average line voltage VRY. Then VYB will be something like this. VYB average, and VBR will be something like this. VYB average. You can see near the peaks, these line voltages also get distorted. This distortion, the pole voltage distortion is there in third harmonic injection PWM technique also, because in third harmonic injection PWM technique, triple N frequency common mode signal MCM is triple frequency common mode signal MCM is injected. And similarly in bus clamping PWM techniques, we inject common mode signals which make pole voltages distorted. But in the line voltages and in the phase voltages, these common mode signals get cancelled. So even if your pole voltage is there, get distorted, but line voltages and phase voltages, which are actual inverter output voltages, they retain their sinusoidal pattern. The instantaneous average line voltages and in the instantaneous average phase voltages in bus clamping PWM techniques and in third harmonic injection PWM techniques, they are sinusoidal. But that is not the case with over modulation. In over modulation, because of over modulation, the pole voltages, instantaneous average pole voltages get distorted, and they will distort the line voltages and phase voltages also. For example, you have seen that line voltages have got a bit distorted here, okay, near the peaks. So low frequency harmonics will be introduced in the line voltages. Same is the case with phase voltages, that's line to neutral voltages. I will now draw the waveforms for three-phase average line to neutral voltages. Line to neutral voltages, which are also called phase voltages. Phase voltages. Line to neutral voltages or phase voltages. So line to neutral voltages or phase voltages will be similar to pole voltages. Like let me first of all draw these inverted waveforms. This may be your pole voltage. This is the phase to neutral voltage VRN, average phase to neutral voltage VRN average. So there is flattening, flat waveform near the peak, pulse dropping. Okay, so similarly it will be something like this. And similar, this is VYN, line to neutral voltage, instantaneous average line to neutral voltage VYN, or instantaneous average phase voltage VYN. And VBN will also be like this. This is instantaneous average phase voltage VBN average. So you can very clearly see that the phase voltages or line to neutral voltages also get distorted. They are at low frequency. There is low frequency distortion or low frequency harmonics reintroduced into these phase voltages, and their pattern is similar to pole voltages. Fine. Now, if you compare this, if you see the comparison between pole voltage, say pole voltage VRO and phase voltage VRN, they are similar. For example, this is your pole voltage. Just few moments back we have seen that this is our pole voltage. This is the pole voltage VRO, average pole voltage VRO average, and your phase voltage is similar to this pole voltage. This is the only amplitude will be slightly higher. This is also flat, slight curvature is there. So this is your phase voltage VRN average. Your pole voltage has an amplitude of 0.5 and minus 0.5, and phase voltage will be slightly higher than 0.5 minus 0.5. Okay, that is about phase to neutral voltages or line to neutral voltages, or what we call as phase voltages. What about now? This is in say sine triangle comparison, sine triangle PWM. Let us try to understand it from space vector perspective. From space vector perspective. From space vector perspective, we know that in space vector plane we have two phase voltages, V alpha and V beta. I will write here now average two phase voltages. Average two phase voltages. So for over modulation, our average, say for under modulation, average two phase voltages are like this. For example, this is V alpha average and this is V beta average in space vector plane. Okay, they are both sinusoidal, but for over modulation, say with m equal to 1.5, they will get slightly distorted. This may be your, this is V alpha average voltage V alpha, and V beta average will be something like this. It will have this type of pattern. This is V beta average. So therefore, if in the space vector plane, the two phase voltages V alpha average and V beta average also, you can say they also get distorted. because of over-modulation. Okay. Now from the space vector perspective, for m equal to 1.1, let us try to see magnitude of average reference voltage vector. Magnitude of average reference voltage vector over a cycle, over a line cycle. We have already studied in space vector PWM when we were studying space vector PWM technique. Our VREF, average reference rotating vector, or average reference voltage vector, which is a rotating vector. जो आपका rotating vector ये है VREF, which traces normally the circular path. Okay, this VREF for a given modulation index is constant. We have seen this while studying conventional space vector PWM technique or bus clamping PWM techniques. So under modulation, when we are not operating our inverter in over modulation mode, it has a fixed value, constant value, and its constant value is given by 4 by pi. Pi by 4. It is given by pi by 4, and pi by 4 is 0.75. Okay, but with over modulation, it's not now constant. It does not remain its magnitude does not remain constant. I mean, when it rotates in the circular path, its magnitude at any point remains constant in the circular path. That's possible only when your inverter is operating in under modulation mode. But when you are operating your inverter in over modulation mode, the reference vector's magnitude is not constant. It does not remain constant at pi by 4 like this. It changes like this. It varies like this. Let me first of all draw, then I will explain. Around 0.8. This line is 0.8. Sometimes it goes above 0.8 and sometimes it goes below 0.8. So this is 60 degrees, sector 1. This refers to sector 1. 60 to 60 is 120 degrees. This refers to sector 2. 120 plus 60 is 180 degrees. So this is with reference to in sector 3. In sector 4, your rotating reference vector magnitude will vary like this. 180 plus 60 is 240 degrees. This is in sector 4. And similarly, sector 4, then this is 240 to 60 is 300 degrees. Sector 5, and finally this is sector 6, 300 to 360 degrees. This is omega t. So you can see for sinusoidal operation of your inverter for under modulation up to a modulation index of 1. Here modulation index m is equal to 1, and here m is not 1. Here m is equal to 1.1. So for modulation index of unity, your rotating reference vector has maximum amplitude. How much? Pi by 4. That's 0.75, and it remains constant because it traces the circular trajectory. When it rotates, traces the circular trajectory and its magnitude remains constant. But as soon as you operate your inverter in over modulation mode, your rotating reference vector, its amplitude increases. Its average value is 0.8, but it in all sectors or in a line cycle, it is not constant like this. It's not constant like this. It varies around 0.8 like this. Sector 1, sector 2, sector 3, sector 4, sector 5, and sector 6. Okay, so this is magnitude of average reference rotating vector over one line cycle, a complete line cycle, 0 to 360 degrees. You can now study it in one sector also. So I will write here magnitude of average rotating reference vector, rotating reference voltage vector over a sector. Not complete line cycle. You can take one sector and you can see how it varies in one sector. So for example, you can take ये 90 degrees है, 90 plus 60 is 150 degree, 150 degree. You can take 0 to 60 degree, or I am taking 90 to 150 degrees. Okay, so this is 90. This is alpha here, alpha is 90 degrees to 150 degrees. And I would like to study the magnitude of rotating reference vector over one sector, say 90 to 150 degrees. ये आपका 0.8 है value. At omega t equal to 90 degrees, it is at 0.8. So it is less than 0.8. So ये यहाँ पे. Then as you move from 90 to 150 degrees, it crosses this 0.8 like this in a sinusoidal manner. Okay, then it goes above 0.8 and then comes down back to this. So this is alpha equal to 90 degrees and this is alpha equal to 150 degrees. Total period is 60 degrees. This is how it varies in one sector. Small value exceeds 0.8, then goes down 0.8, and then it repeats in other sectors. Okay. Now, what about the angle? What about the variation of angle of average vector? Your average vector, sometimes average reference vector is sometimes here, sometimes it is here. I mean, with respect to alpha, this is angle, then this is the angle, sometimes it is here. As it moves from one place to another place, the angle increases. Let us see how, let us see the variation of angle of rotating reference vector over one sector. Variation, I will write here, variation of angle of rotating reference voltage vector over one sector. We can again take one sector, say you can take 90 degrees to 150 degrees. So this is 90 degrees, this is 150 degrees. And I would like to now plot, this is omega t. I would now like to plot angle of rotating reference vector. You can see this angle varies linearly over this sector. It varies linearly. This is the variation of angle. क्योंकि आपका rotating reference vector ऐसे, it moves like this. No doubt, it sometimes its magnitude is high, sometimes it is low, but it moves at a linear speed, at a constant speed. So its variation of angle of rotating reference vector is linear in one sector, and hence it is linear over entire, this line cycle. I will write here linearly varying with time. It's linearly varying with time. Okay, fine. Now let us draw the space vector diagram, and from space vector diagram we will see what type of voltage vector is applied across the load. So I will write here average voltage, average reference voltage, or average voltage vector applied across load. Our space vector diagram is like this. This is our active vector 1 with switching sequence plus minus minus. This is active vector 2 with switching sequence plus plus minus. This is active vector 3 with switching sequence minus plus minus. This is active vector 4 with switching sequence minus plus plus. Similarly, this is active vector 5 with switching sequence minus minus plus, and this is active vector 6 with switching sequence plus minus plus, and then we have two null vectors, null vector 0 with switching sequence minus minus minus, and null vector 7 with switching sequence plus plus plus. If I join the tips of these space voltage vectors, I get a regular hexagon like this. We already know this. And our rotating reference vector is rotating within this hexagon. Okay, now for under modulation, in fact after modulation index of unity, it rotates and it traces the circular path. But just few moments back you have seen that in one particular sector or over a line cycle, if this is rotating reference vector magnitude Vref, it varies like this. It's not constant like this. Okay, rotating, if you start from here, rotating reference vector has maximum amplitude here. So it has maximum amplitude here. Say for example, it has this much of amplitude here. Let me call this Vref1, and it is along alpha axis. ये आपकी alpha axis है. Then as it rotates, I mean by time averaging, this is your sector 1, by time averaging of these vectors, two active vectors and null vector, you produce a rotating reference vector. Now this rotating reference vector, as you know, as you take more and more samples, you time average these three vectors. For next sample, you can see its magnitude now reduces. It has less magnitude. So for next sample, it's somewhere here. It's less than this. So it's somewhere here. Let me call this Vref2. Vref2. When you take third sample, it further decreases. This is Vref3. And then it is minimum here, somewhere in the middle, say 30 degrees back. It's minimum in the middle. Excuse me. Here it is minimum. उसके बाद आप देख सकते हैं it increases as it sweeps sector 1. 30 degrees से 60 degree तक. Its amplitude increases, it increases, or finally, when it is along, you know, reference vector 2, its amplitude is maximum again. So Vref1 is high, Vref1, Vref2 is less than Vref1, Vref3 decreases, then further decrease, then it starts increasing. Okay, and if you join the tips of these rotating reference vectors, will it trace circular path? No, because Vref1 is this, Vref2 is this. This is Vref2. Vref3 is this. This is Vref3. Vref4 is this. Let me call this Vref4. Then it starts increasing again. This is Vref5. Then this is Vref6. And this is Vref7. If you join the tips of these rotating reference vectors, what type of path? It does not trace circular path. It traces circular path only when you know, it operates in under modulation mode up to a modulation index of 1, 0 to 1. But when you are over modulating it, you have just now seen in each sector the magnitude of rotating reference vector varies. It's high, then it decreases, then it increases again around 0.8, something like. And if you join the tips of these rotating reference vectors, it does not trace a circular path. It is a non-circular path. And when rotating reference vector does not trace a circular path, when its trajectory is non-circular, that is an indication of distortion in inverter output voltage. If rotating reference vector is rotating in a circular path, then that means inverter output voltages, their average values are sinusoidal. They are sinusoidally varying. But if it does not trace circular path, it traces non-circular trajectory, it means that inverter output voltage has some low frequency distortion. Okay, some low frequency harmonics get again injected into the inverter output voltage. So no doubt you are able to increase inverter output voltage by over modulation, but at the cost of low frequency distortion. Okay, so tip of Vref, so I can write here magnitude or amplitude of Vref1 is not equal to magnitude of Vref2. It's not equal to magnitude of Vref3, and so on. Right? So let us summarize what we have learned for modulation index equal to 1.1. Let me give you summary. First point is no, I will note down here, no or one sinusoidal modulating signal exceeds the peak of carrier signal, carrier cycle. If you take one carrier cycle, in this one carrier cycle, like this, you are comparing three sinusoidal only one sinusoidal modulating signal may be higher than peak of triangular carrier wave, and in some other carrier cycles there will be no sinusoidal modulating signal greater than the peak of the carrier cycle. At the most only one, because depth of modulation, over modulation, is very, very low. Okay, so therefore either no more sinusoidal in one particular carrier cycle. If you consider one particular carrier cycle and comparing it with 3 modulating sinusoidal waves, you will find that no modulating sinusoidal wave in one particular carrier cycle will be exceeding the peak of the carrier cycle, or at the most only one sinusoidal modulating wave will be exceeding the peak of a carrier cycle. Peak of a carrier in a carrier cycle. This is first observation. Second observation is pulse dropping. Pulse dropping means the instant when a particular modulating sinusoidal wave is greater in amplitude than triangular carrier wave, and that particular phase leg is clamped to either positive DC bus or negative DC bus, and during that period there is pulse dropping. No pulses are produced at the inverter output voltage. No notches are there. It's called pulse dropping. Pulse dropping occurs around peak of fundamental voltage. Around peak of fundamental voltage in each phase. We have seen that pulse dropping occurs only near the peak for phase pole voltage VRO, for pole voltage VYO, and for pole voltage VBO. Similarly for phase to neutral voltages also. Pulse dropping occurs only near the peak of the fundamental voltages in each phase, whether it is phase R, phase Y, or phase B. Okay, that's second point. Depth of, third point is that depth of OM means over modulation, is not very high, which means that is when pulse dropping of one phase leg or one phase ends, the pulse dropping of some other phase starts. At any instant of time, you have seen through those waveforms, but at any instant of time, only one phase leg will be clamped to positive or negative DC bus. Or in other words, in terms of pulse dropping, there will be pulse dropping of only one phase leg. And when pulse dropping of that phase leg is over, then pulse dropping of another phase leg will start. When pulse dropping of next phase leg ends, then pulse dropping of third phase leg will start. So at any instant of time, only pulse dropping will be there for only one phase leg. Okay. Then low frequency distortion, in average pole voltages, line voltages, and phase voltages occurs. Phase voltages occurs. We have seen that because of over-modulation, your instantaneous average pole voltages get distorted. That causes distortion in instantaneous average line voltages and instantaneous average phase voltages. And hence low frequency distortion is introduced in inverter output voltage. Okay. Then magnitude of average reference vector, I will write here magnitude of average rotating reference vector, जिसको हम VREF भी कहते हैं, VREF varies with fundamental angle. We have seen over one line cycle, your reference vector varies like this. It's not constant. It varies in each sector and over complete line angle. So it varies. It's not constant. It varies with fundamental angle. Okay. And then we have seen that the trajectory, next point is trajectory of tips of reference vector is non-circular, because at an instant of time your reference vector may have some high value, and as then you take more and more samples, its magnitude may decrease first, then it may increase. First VREF1 is higher, then VREF2 is lower, VREF3 is still lower, then it is higher, then it is higher. So the trajectory of the tip of the rotating reference vector, it's not circular, it is non-circular, which means that low frequency distortion is introduced in inverter output voltage. And finally, angle of average reference rotating vector varies linearly with time or with fundamental angle. We have seen, and we have seen through the waveform also, that the angle alpha varies linearly. Okay, the magnitude of reference vector varies. It varies with time or with angle, but its angle it does not change. Angle varies linearly. It varies in a linear fashion. So that is for modulation index in the range 0, greater than 1.0 but less than 1.15, and we have taken a modulation index of 1.1. Let us now try to study for slightly higher modulation index, a different range of modulation index. Okay, now we will study over modulation in the range 1.15 less than m less than 2.0. Now we will assume that our modulation index of inverter is greater than 1.15 but it is less than 2.0. Let us take a particular modulation index greater than 1.15. Let us take m equal to 1.2. Okay, so therefore our modulating sinusoidal waves will be like this. This is MR. Sorry. This is MY and this is MB. This is MB. This is a modulation index of 1 here. Say somewhere here we have a modulation index of 1.0. This is 1.2. So peak of each peak of each sinusoidal modulating wave, MY, MR, MY, MB, it is 1.2. You can see it's greater than 1. And we are considering this range and we have taken m equal to 1.2. So therefore there will be, आपकी carrier wave, for example, यहाँ पे है, this is your carrier wave. Similarly, ठीक है. So you can see from this instant to this instant, the modulating wave MR is greater than triangular carrier wave. Okay, so from this instant to this instant, there will be bus clamping, or in other words, there will be pulse dropping from this instant to this instant. Okay, so therefore, so for example, pole voltage, instantaneous average pole voltage VR will increase in the same manner as MR, because I have told you that average pole voltages are scaled versions of sinusoidal modulating waves. So from here to here, your average pole voltage VRO will increase in the same manner, but then here it will get clamped. Okay, so it will be flat like this, because from this instant to this instant, top switch of phase leg R will be permanently on, and pole voltage VRO will be equal to 0.5 VDC or VDC by 2. There will be no switching from this instant to this instant, so that will cause pulse dropping. Similarly in the negative half cycle and so on. Okay, so this is about, these are the three reference modulating sine waves, MR, MY, MB for modulation index 1.2. What about three-phase average pole voltages? I will write now three-phase average pole voltages. Let us draw three-phase average pole voltages. Excuse me. So I will draw average pole voltage VRO average. So this is instantaneous average pole voltage VRO average. What about VYO average? VYO average will be something like this. This is VYO average pole voltage, VYO average, and VBO average will be like this. This is VPO average. So there is pulse dropping here, 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 similarly in the negative half cycles. Now you can very interestingly see that during this instant, this if you take this region, in this region from here to here, there is pulse dropping in phase leg R, so that VRO is equal to 0.5. It is VRO is equal to 0.5 here. And simultaneously during this small period, there is pulse dropping taking place in phase leg Y also, so that VYO is equal to minus 0.5. And then from here to here, there is pulse dropping of only R phase. There is no pulse dropping of Y phase, no pulse dropping of B phase. That means Y phase and B phase, they switch from this interval to this interval. R phase leg and Y phase leg, they are clamped to positive and negative DC buses respectively, and there is pulse dropping of both the legs. Whereas phase leg B switches, you can see phase leg B switches during this time period. Whereas from this instant to this instant, only phase leg R has pulse dropping, whereas phase leg Y and B, they switch. And then from, you can see, from this instant to this instant, यहाँ से यहाँ तक आप देख सकते हो, over this small region, there is pulse dropping of phase leg B also, you can see. Phase leg B also has pulse dropping. So therefore, there is pulse dropping of phase leg R, there is pulse dropping of phase leg B also. But whereas phase leg Y switches, you can see during this period, phase leg Y switches. Okay. So in this small region, I will write both R phase and Y phase pulse dropping. Then during this interval, यहाँ से यहाँ तक, only R phase has pulse dropping, And during this interval, R phase and B phase has pulse dropping. I will write here R phase during this period, R phase and B phase, they have pulse dropping. So therefore इसमें आप देख सकते हैं the difference between m equal to 1.1 and m equal to 1.2, that is the previous range of modulation, over modulation, 1.1 less than m less than 1.15, and this range of over modulation, that is 1.15 less than m less than 2.0. Here I have taken m equal to 1.2, is that there are certain regions, certain time intervals for which two phase legs have pulse dropping and third phase leg switches. Like during this period, R and Y phases have pulse dropping, B leg switches. During this period, R and B phases have pulse dropping and Y leg switches. And during this period, only R phase has pulse dropping, whereas Y and B phases switch. So this is the, whereas in the previous case, we have found that at any instant of time, only one phase leg has got pulse dropping. The other two phase legs switch. But here in this case, we have certain intervals of time when two phase legs will have pulse dropping and third phase leg will be switching. Okay, so this is instantaneous average pole voltages, VRO average, VYO average, and VBO average. So let us quickly draw the instantaneous average line voltages now, waveforms for line voltages. Three phase average line voltages. Line voltages. Suppose this is 1.0 and this is minus 1.0. Let's try to see line voltages. This will be our line voltage VRY. This is average line voltage VRY average. Then line voltage VYB will be like this. This is average line voltage VYB average, and VBR will be like this. This is average line voltage VBR. You can very clearly see near the peaks there is some distortion in the voltage. From here to here the waveform is sinusoidally varying. From here to here it is sinusoidally varying, but near the peak here, positive peak and negative peak, there is some slight jump and it varies non-sinusoidally. Each line voltage, VRY average, VYB average and VBR average, they get distorted near the peak. This is the same type of waveform as we have seen for m equal to 1.1. The only difference being their peak of each line voltage was less than 1.0. Here peak is equal to 1.0. So this is three-phase average line voltages. So we can see in three-phase average line voltages also, sort of distortion is introduced. There is distortion in the line voltages. And now three-phase average phase voltages, or line to neutral voltages. Three-phase average phase voltages, VRN, VYN and VBN average. They will be similar to pole voltages. They will follow the pattern of pole voltages. So this is your VRN average. this is phase voltage VYN average, and this is phase voltage VBN average. VBN average. It has same pattern as pole voltages. The only difference between phase voltages and pole voltages I can explain like this. For example, this is your pole voltage. This is 0.5 minus 0.5. This is your pole voltage, VRO average pole voltage. Average phase voltage VRN will be slightly greater than this. It will have same pattern as this, लेकिन इसका peak थोड़ा greater होगा. It will be greater than 0.5. So this is VRN average. So its waveform is similar to average pole voltage. Only its peak is slightly greater than 0.5. That's it. So that is three-phase average pole voltages. Now let us try to analyze. So you have seen that whether it is three-phase average pole voltages or three-phase average line voltages or three-phase average phase voltages, over-modulation causes distortion, low frequency distortion in the voltages. No doubt inverter output voltage increases, but at the cost of low frequency distortion. Let us try to analyze it from the perspective of space vector. Okay, so first point that we are going to discuss is average reference voltage vector, magnitude. Right here, magnitude of average reference rotating vector Vref over a cycle, over a line cycle. We'll first of all see how it varies over a line cycle. This is our omega t 0 degree. So this is, again, as I have already told you, this is for modulation index m equal to 1.0, and this is 0.8. Here the magnitude is Vref. This is our Vref. Magnitude of Vref for modulation index 1 is 0.75, but reference vector is constant over entire line cycle. And this is 0.8 line. This line is 0.8 magnitude. And our rotating reference vector varies like this. Let me first of all draw, then I will explain. And 6. Okay, so this is sector 1, sector 2, 3, 4, 5. This is 0.866, this value, 0.866. So you can vary, you can see that in first sector, sector 1, so there's 0 to 60 degrees. This is sector 2, 60 to 120 degrees. This is sector 3. Sector 2, sector 3, sector 4, sector 5, and this is sector 6. In first sector, your rotating reference vector is not constant. Its amplitude is not constant like this, as it was for modulation index equal to 1. For over modulation, this is for m equal to 1.2. Rotating reference vector magnitude varies in each sector like this. First it is 0.866, then it drops in the middle 30 degrees, it drops to 0.8, then it rises again. Then in same pattern it follows in other sectors. Okay, so therefore you can see it in one sector. You can take just one sector. This is magnitude of average reference rotating vector over one cycle. So magnitude over a sector. Let us see its magnitude over one sector, how it varies over one sector. Say 90 degrees to 150 degrees. So this is 90 degrees. This is 150 degrees. Okay. आप देख सकते हैं, this is when it is 90 degrees, it has the value of 0.8. ये आपका 0.8 है. And as you move from 90 to 120 degrees, it increases. 90 to 120 degree, it increases. Then 120 to 150 degree, it decreases again like this, decreases again. So this is 150 degrees. So this is how its magnitude varies from sector to sector. Okay. What about angle? Next is angle of rotating reference vector over a sector. एक सेक्टर में आप देखिए इसका एंगल कैसे वेरी करता है. I will again take omega t, say this is also omega t axis, 90 to 150 degrees. From 90 to 150 degrees, its angle varies like this. There is a slight deviation, but more or less it remains linear. This is alpha. So this is 150 degrees. Your rotating reference vector moves at a linear speed. You can see it is nearly linear. Nearly linearly varies. Linearly varies. So angle is nearly linear. So that means your rotating reference vector moves at a constant speed. Its angle varies linearly over one sector and similarly over other sectors. So based on this, what is the average voltage vector applied to your load? Let us see average voltage vector applied to the load. Average voltage vector applied. Applied means applied across the load. So अभी थोड़ी देर पहले हमने देखा, it's like this. In one sector, in other sector, this is 0.866, then this is 0.8 and so on. So let us draw the space vector diagram first. This is the active vector 1, active vector 2, active vector 3, active vector 4, active vector 5, active vector 6, null vector 0 and null vector 7. This is regular hexagon. When you join the tips of these space voltage vectors, you get hexagon like this. For under modulation and up to a modulation of m equal to 1, your rotating reference vector, when it is sampled by in a particular sector by time averaging of 3 vectors, it moves with each sample, it moves in and traces a circular path, and its amplitude is constant. Constant amplitude means it moves in a circular trajectory. It makes circular trajectory. It moves linearly like this, traces this circular path, and magnitude remains constant. But just few moments back, we have seen that in each sector, its magnitude is not constant. For example, when you start, say you take the sector 1 at alpha equal to, this is alpha equal to 0 degree, its magnitude is maximum. So it will have maximum magnitude, say this is your VREF1. Then as you move from 0 to 30 degrees, magnitude decreases with each sample. Its magnitude varies. This is VREF2. Its magnitude further decreases. Its magnitude is minimum at alpha equal to 30 degrees. Then as you move from 30 to 60 degrees, its magnitude again increases. It increases, and it is maximum here. Okay, so therefore magnitude of rotating reference vector with each sample, it is not constant. It varies in a sector, and it varies from it varies in a similar fashion in each sector. Okay, so this is the type of voltage vector which is applied or applied across the load. So since some of the rotating reference vectors, they have higher amplitude, so this impresses higher voltage across the load. But at the cost of what? At the cost of low frequency distortion, because if you join the trajectory of these rotating reference vector, the tips, this is the tip of VREF1, tip, you join the tips, it's not circular trajectory, it is non-circular trajectory, which means that low frequency distortion is introduced in inverter output voltage. So again, you could write VREF1 is not equal to VREF2 and so on. Okay, so let us summarize for this modulation index. Let me give you a summary for m equal to 1.2 over modulation. Summary. First point is that 1 or 2 modulating signals, one or two modulating signals exceed carrier peak, in a carrier cycle. For lower modulation index m equal to 1.1, I mean over modulation, but m equal to 1.1, first range, which we have discussed few minutes back, we have found that either one or no modulating signal may exceed the carrier peak in a carrier cycle. But for m in second range, 1.15 to 2, for example, here we have taken m equal to 1.2. In one carrier cycle, one modulating wave or more than one, that is one or two modulating waves, their peaks may exceed the carrier peak in a carrier cycle. Okay, this is one difference. Second is pulse dropping is 60 degrees to 120 degrees. Pulse dropping interval is from 60 degree to 120 degrees. For example, for modulation index equal to 1.15, pulse dropping occurs for, it is 60 degrees. Pulse dropping interval is 60 degrees. And for m equal to 2, it is 120 degrees. Since we are considering this range of modulation index, 1.15 less than m less than 2, that is greater than 1.15 but less than 2. So it will be 60 degrees to 120 degrees. Greater than 60 degrees but less than 120 degrees. Okay. So that means the interval, the period of pulse dropping has increased. And then third important point is that low frequency distortion in average pole, line and phase voltages occurs. We have seen because of pulse dropping, average pole voltages, average line voltages and average phase voltages, their low frequency distortion occurs. Okay. The next point is magnitude of rotating reference vector. I should write Vref. Now Vref is understood, it is rotating reference voltage vector. So magnitude of average rotating reference vector, Vref, varies with alpha. Okay. And next is that trajectory of tip of Vref is non-circular. It's again non-circular, which means low frequency distortion is there in the inverter output voltages. And finally, angle of rotating reference vector Vref varies linearly with time or with fundamental angle. So these are some of the observations. I have summarized what we have learned for this range of over-modulation. Over-modulation range was 1.15 less than m less than 2.0. And we had taken m equal to 1.2, which is greater than 1.15 but less than 2. And these are, when we compare it with the previous over-modulation range, what was that? 1 less than m less than 1.15. We had taken m equal to 1.1, which is greater than 1 but less than 1.15. Their first point was that in one carrier cycle, only one or no modulating signal may exceed carrier peak. But here, for this over-modulation range, in one carrier cycle, one or two modulating signals may exceed carrier peak because the depth of over-modulation is increasing. Then pulse dropping there was less than 60 degrees. Here it is 60 to 120 degrees. Then low frequency distortion in average pole voltages, average line voltages and average phase voltages was introduced in this range also, in this over-modulation range, and that will be in this over-modulation range also. Then there also we found that magnitude of Vref varies with alpha. Here also it varies with alpha. No doubt here the magnitude of Vref varies like this. Okay, it is 0.866 to zero point 0.8, like this, 0.866, then 0.8, then back to point. There it was like this. There it was slightly greater than 0.6, 0.8, but less than 0.8. Here it does not go below 0.8. So magnitude is higher. There also we found that trajectory of tip of reference vector is non-circular. Here also it is non-circular. And there also we found angle of VRF varies linearly with time or fundamental angle. Here also same observation. So here for m equal to 1.2, inverter output voltage further increases, but distortion level also increases. Let us take m equal to 2. We will take over modulation with m equal to 2.0, m equal to 2. So three-phase reference, target reference signals or three-phase sinusoidal modulating waves will be something like this. Three-phase modulating waves will be like this. This is MR and its peak value is 2.0. This is sinusoidal modulating wave MY, and this is sinusoidal modulating wave MB. Excuse me. We should touch this. This is MB. Now, what is this? This is 1.0. This line is 1. This value is 1.0. Now you can see in this case, this angle is यहाँ से यहाँ तक ये 30 degrees है. This is 30 degrees to, if you see up to this point, this is 90 degrees. This is 30 degrees to 90 degrees. From 30 degrees to 90 degrees here, since MR is greater than 1, so phase lag R will have pulse dropping. Simultaneously, since My is also greater than -1, this is -1. So phase lag Y will also have pulse dropping. So that means and what about phase lag B? Phase lag B is less than 1.1, less than 1, so it will switch. So that means from 30 to 90 degrees, that means in this 60 degree interval, आप देखेंगे थे, phase lag R will have pulse dropping or bus clamping, and phase lag Y will also have bus clamping or pulse dropping, whereas phase lag B switches. That means at any instant of time, two phase legs will be simultaneously clamped to DC buses, or there will be pulse dropping in two phase legs, and only one phase leg will be switching. So for 60 degree range, two phase legs have pulse dropping. That means bus clamping. And only one phase leg switches. Example I have given you here. Okay. So two phases are clamped and third phase leg switches. Okay. We can take next 30 degree interval. Next 30 degree interval, 60 degree interval, sorry, 90 to 150. During this period, phase leg R again has pulse dropping, and phase leg B now has pulse dropping, whereas phase leg Y switches. So in each 60 degree range, two phase legs will be clamped, bus clamped, or two phase legs will have pulse dropping, and only one phase leg will be switching. So this is about three-phase sinusoidal reference waves. And now let us draw three-phase average pole voltages. Three-phase average pole voltages. In order to give a better view, let me use a red color pen for phase leg R. Excuse me. This is 0.5 and this is minus 0.5. This is average pole voltage, VRO average. What about VYO average? VYO average will start from here. Will start from here. VYO average will start from here. This is VYO average. I can again use, I don't have unfortunately blue color pen. Let me use red color pen again for VBO average. For VBO average. Okay, VBO average will be something like this. This is VBO average, and similarly here it will go like this. This is VBO average. So we have three average pole voltage: VRO average, VYO average, and VBO average. So you can see, the time interval for which pulse dropping is there, it increases because your modulation index is now very high, it's 2.0. The period for which your modulating reference waves are greater than peak of the carrier wave, that period increases. So the period of bus clamping or period of pulse dropping also increases. So obviously the inverter output voltage magnitude will also increase, no doubt. But the level of distortion will also increase in inverter output voltage. We'll see that also. So this is about three-phase average pole voltages. What about three-phase average line voltages? Let us draw the waveforms for three-phase average line voltages. Our three-phase average line voltages will be something like this. So this is 1.0. This is minus 1.0. So this is our line voltage, average line voltage, VRY average. What about VYB average? VYB average will start after 120 degrees. It will be something like this. This is VYB line voltage average, and VBR will be like this. VBR average. This length should be same. I'm sorry if these are drawing inaccuracies. You can correct them yourself. In the previous case, for m equal to 1.2, the line voltages were like this. It was clamping to, it was equal to 1.0 for a very small period of time. But in this case, since modulation index is very high, it has increased from 1.2 to 2.0. The period for which your three line voltages, they are equal to 1.0, that period increases. So that will increase the line voltage, the magnitude of line voltages applied across the load. Okay, because the period for which your line voltages stay at 1.0, that increases. So that increases the RMS value of inverter output voltage as far as line voltages are concerned. Let us quickly draw three-phase average phase voltages or line to neutral voltages. Three-phase average phase or line to neutral voltages. So they are like this. So this is our, say for example, this is ये वाला point, this is 0.6 and this is minus 0.6. This is our, now you can see your phase voltages are not following pole voltage pattern because modulation index is very large. Your phase voltage VRN average, it's piecewise linear. It's linear line, then linear, then like this, piecewise linear. So I will write here piecewise linear. For example, positive half comprises of 1 line, 2 line, 3, 4. Similarly, negative half cycle. So this is VRN average. Similarly, VYN average will be like this. This is VYN average, and VBN average will be like this. Sorry. This is pole voltage VBN average. Now if you compare, sorry, not pole voltage, phase voltage VBN. If you compare pole voltage VRO with pole phase voltage VRN, now they are totally different. You can see, for example, this is your pole voltage. This is your average pole voltage, VRO average, 0.5 minus 0.5. And your phase voltage for phase leg R, VRN, is something like this. Something like this. This is your phase voltage VRN average. So it is different. Okay. And its peak value is around 0. It's not exactly 0.6, it's around 0.6. So you can see average phase voltage is totally different from average pole voltage. This is the effect of higher modulation index. Okay. Now let us see it from space vector perspective. From space vector point of view, we'll write magnitude of Vref over a cycle. Now Vref will again vary with angle or with fundamental time, but its magnitude will further increase. It will increase like this. Sector 1, Sector 2, Sector 3, Sector 4, Sector 5, Sector 6. This is 360 degrees. This is 0 degree. This is 60 degrees. 120, 180, 240, 300. Sector 1, Sector 2, Sector 3, Sector 4, Sector 5, and Sector 6. Fine. So this is 0.8 and this is 1. And for m equal to 1.2, it was like this. It was varying from 0.866 to 0.8. Now its amplitude further increases from 0.866 to 1. Okay, but it varies. You can see it again varies. It's not constant. It is for modulation index equal to 1. For example, this is for modulation index equal to 1. It is constant, 0.75. But for, this is for modulation index equal to 2. It is not constant. It is varying. But its peak value has further increased. So if you see the magnitude over one sector, magnitude of Vref over one sector, एक सेक्टर में अगर आप Vref का magnitude देखेंगे, say you see it from 90 degrees to 180 degrees, something like this. Actually can start like this. 0.8 से आप start कर सकते हैं. It varies like this. 90 degrees, 150 degrees. This is 0.8 and this is 1.0. It varies like this. It's high, then it decreases, and so on. And what about variation of angle? variation of angle of Vref over a sector. This is 90 degrees to, say, for example, 150 degrees omega t. There is slight variation in alpha, but it is almost linear. So nearly linearly varying. Nearly linearly varying. Let us see what type of voltage vector is applied now across load from space vector point of view. Average voltage vector applied across the load. Average voltage vector will be like this. This is active vector 1, draw space vector diagram first, active vector 2, active vector 3, active vector 4, active vector 5, active vector 6, null vector 0, null vector 7. This is space vector. When this is hexagon when you join the tips of these space voltage vectors, and you can see your reference voltage vector moves along these triangles. Along, this is Vref1. So for example, this is Vref1, this is Vref2, Vref3, and so on. Vref4, 5, 6, and so on. So your Vref moves along the sector 1 boundary. This is your sector 1, sector 2, sector 3, 4, 5, 6. And when you join the tips of these space voltage vectors, you get a hexagon. So your reference voltage vector moves along the boundary of hexagon or triangles. In sector 1, sector 2, like this, it will move along this. Here it will have some magnitude, here it will have different magnitude, here it will have different magnitude, and all that. But as far as this angle is concerned, the angle does not change. It varies linearly. Okay, it varies linearly. At same speed it moves. Right? This is the nature of voltage vector that gets applied across the load, and you can very interestingly see when it moves along the boundary of the hexagon, no null vector is applied. Only active vectors are applied. I should write here, no null vector is applied. Only active vectors. For example, in sector 1, active vectors 1 and 2 are applied. Null vector, neither null vector 0 nor null vector 7 is applied. Only active vectors are applied. For example, this active vector has switching sequence of plus minus minus. This active vector 2 has a switching sequence of plus plus minus. You can see R phase is plus here, R phase is plus here. Since null vector is not applied, so we will not consider null vector. B phase is minus here, B phase is minus here. So that means R phase is clamped to positive DC bus. So there is pulse dropping in R phase. B phase is clamped to negative DC bus. There is pulse dropping in B phase also. Whereas Y phase switches. This is because Y phase has status of plus here, minus here. So R phase, R and B phases, they have pulse dropping. That means they are clamped to positive and negative DC buses respectively. Whereas only one phase switches. Whereas Y phase switches in sector 1. Similarly, you can find status in other sectors. So in any sector at any instant of time, you will see that, and you have seen through the waveforms also just a few minutes back, at any instant of time over this 60-degree interval in each sector, two phases have pulse dropping and only one phase switches, and no null vector is applied, right? So let me write the summary of what we have found for over-modulation with m equal to 2.0. So summary is like this. We'll summarize. Two modulating signals exceed the carrier peak in a carrier cycle. For over-modulation range 1.15 less than m less than 2, which we have discussed before this, we have found either one or two modulating signals exceed carrier peak in a carrier cycle. But for m equal to 2, two modulating signals exceed the carrier peak in a carrier cycle. Remember this. Second point is pulse dropping occurs in two phases and only one phase switches. Only one phase switches. This is an observation just we have made just few moments back. Okay, and then third observation is that switching between active states only, no zero state is applied. For example, in sector 1 you have seen that only active vector 1 and active vector 2 they are applied. Null vector 0 or null vector 7 is not applied. Same is true with other sectors also. Then pulse dropping for 120 degrees in each half cycle of each phase. In each half cycle of each phase, phase R, phase Y, phase B, there is pulse dropping for a period of 120 degrees. Okay, so this is pulse dropping is for a larger period. The line voltages and phase voltages, they will have higher amplitude now. Okay, then low frequency distortions will be more here. Low frequency distortion will be there in average pole, average line, and average phase voltages occurs. And the level of distortion for m equal to 2 will be higher than previous case. Then next is magnitude of reference rotating voltage vector VREF varies with alpha. With alpha we have seen it varies like this in each sector. And then we have seen angle of VREF varies linearly. Varies linearly with time. Varies linearly with time or fundamental angle. Or fundamental angle. And finally, trajectory of tip of VREF is non-circular. And it is in fact hexagonal. VREF traces this path, hexagon. You have seen it just few moments back. VREF moves along the hexagon like this. Okay, so trajectory is hexagon. So that is about m equal to 2. Let us take now last very high modulation index over modulation with m equal to 3.0, which is fairly high modulation index. Okay, so your three-phase modulating sinusoidal modulating waves will be like this. This is MR, peak value is 3.0, and positive peak and negative peak is minus 3.0. This is MY and this is MB, right? Oh yeah, आपका 1 है. This is 1. So this is 3 times this. आपका carrier ये होगा 1 to minus 1 like this. 1 to minus 1 to minus. But this is now you can see the period for which your modulating wave, MR, is higher than carrier wave. It's very, very large. It's from 30 degrees to 150 degrees. So that means 120 degrees तक ये है. Pulse dropping occurs for about 120 degrees in positive half cycle and 120 degrees similarly in negative half cycle. Okay, so pulse dropping interval is now increased. Depth of over-modulation increases. Let us quickly draw three-phase average pole voltages. Three-phase average pole voltages. Okay, very quickly we will draw three-phase average pole voltages. So these will be something like this. R phase, for a very large period, pulse dropping is there, and R phase is clamped to positive DC bus, 0.5. This is VRO average pole voltage, VRO. What about V by O? V by O will start from somewhere here. V by O average, and VBO, I will again use red, black color pen. VBO is something like this. This is VBO average. So these are average pole voltage. You can see the pulse dropping interval increases substantially. Okay, so this is three-phase average pole voltages. Now let us quickly draw three-phase average line voltages. We are slowly moving towards square wave mode of operation, slowly and gradually. Ultimately, for a very large modulation index, for very large, this over modulation, we will end up with square wave mode of operation. Three-phase average line voltages. So three-phase average line voltages will be like this. This is line voltage VRY average, and 1.0 and minus 1.0. So it is at 1.0 for a very large interval of time. Okay. Similarly, this is VYB, line voltage VYB average, and this is VBR. Sorry, it will be 0 for some time. So this is VBR average. So you can see the RMS value of line voltage will be now much higher than previous case, because it stays as at 1.0 for a fairly long period. So that increases the fundamental component of RMS value of fundamental component of inverter output voltage. Let us quickly draw three-phase average phase voltages. Three-phase average phase voltages. So our line to neutral voltages or phase voltages will be like this. So this is phase voltage VRO, phase voltage VRN average. Okay. What about VYN average? Our VYN average will be like this. It will also stay here. This is VYN average, and VBN average will also be like this. It will stay here. So this is VBN average. If you compare any phase voltage, VRN average, with corresponding pole voltage, these will be totally different with respect to each other. For example, this is our pole voltage, VRO average with 0.5 and minus 0.5. Our phase voltage is like this. This is, sorry, it has to be outside this. So this is our phase voltage, VRN average, and this is 0.6. So you can see it is totally different. It's almost 6-step operation. Well, let us see from space vector perspective. We'll see magnitude of rotating reference vector Vref over a cycle. So it is like this. This is 0 degree. This is 0.8. So it is like this. Two, three, four, five. 1, 2, 3, 4, 5, 6. So this is sector 1, sector 2, sector A, and this is 1.0. You can see your rotating reference vector, it starts from 0.8, and with the passage, this is here, say 360 degrees. In sector 1, then it increases, then it reaches maximum value 1, and it stays at 1 for a fairly long time. And then it comes back, comes down, and like this. Okay, if you see over one sector, magnitude over one sector, magnitude of Vref over one sector, एक सेक्टर ले लीजिए, कोई भी एक सेक्टर ले लीजिए, say 90 degrees to 150 degrees. If you take omega t 150 degrees, so it is like this. Vref varies like this. It is 1.0, and then it is again 1.0, and here it is 0.8. Okay, this is how it varies. So what about angle? Now angle does not vary linearly. Variation of angle of reference rotating vector over a sector or in a sector. We can take again, this is omega t, 90 degrees to 150 degrees, and this is alpha. It's something like this. It remains here, and it goes like this, then it remains here. This is 90 to 150 degrees. Okay, here vector 1 is applied. Vector 1 only is applied. Here only active vector 2 is applied. 2 is applied. Here both 1 and 2 are applied. I mean, what happens? Angle is like this. You start from here. Okay, it starts from, say, alpha rotating, and then it stays at active vector 1 for fairly long time. That means it does not, alpha does not change. It remains constant. And then there is switching between 1 and 2. Switching between 1 and 2 active vectors takes place, and then angle increases linearly. And when it reaches close to, when it reaches 2, it remains at 2 for fairly long time. So here, when it is at 2, it remains there for some time, and during that period angle does not change. And similarly, when it starts from active vector 1, it remains there for some time, angle does not change. And in between, angle changes linearly, because during this period both active vectors 1 and 2 are applied. So it will be clear to you with the help of space vector diagram. So I will write now average voltage vector applied. Average voltage vector applied. This is active vector 1, active vector 2, active vector 3, active vector 4, active vector 5, and finally active vector 6. This is null vector 0, null vector 7. So this is our hexagon. Our reference vector starts from active vector 1. This is vref 1, and it stays for a longer time. I mean, how do you generate this active vector, this vref 1? By applying active vector 1 only. 2 is not applied, null vector is not applied at all. So active vector 1 with switching sequence plus minus minus is applied, and it stays there for a fairly long time. And during this period, we have just few moments back shown that angle does not change. And then it's switching between 1 and 2 occurs. So active vector 1 is applied, then active vector 2 is applied, and time averaging of the two produces, in one sample, produces reference vector vref 2. Then 3 vref 3 vref 4, depending upon kitne samples आप लेंगे. And finally, when it reaches active vector 2 along this, it remains or it stays here for a long time. So during this, angle varies. Active vector 1 पे काफी time रहता है, so angle does not vary. And then sampling of active vector 1 and 2 occurs, and rotating reference vector, moves. Alpha increases linearly. Then it stays at active vector 2 for a fairly long time. So this is how alpha varies with respect to time or with respect to fundamental angle. So no null vector is applied. Here in this case, no null vector is applied. Okay? We start with active vector 1. Active vector 1 is applied for very long time, and then switching between 1 and 2 occurs, and your rotating reference vector rotates like this. And then when it reaches active vector 2, it remains at active vector. That means active vector 2 is again applied for a fairly long time. Same happens in other sectors. Okay, so therefore, let us summarize our findings. Summary. First point is that 2 or 3 modulating signals, 2 or 3 sinusoidal modulating signals exceed carrier peak in a carrier cycle. Whereas for m equal to 2, with over-modulation m equal to 2, we have found only 2 sinusoidal modulating signals exceed carrier peak in a carrier cycle. But for m equal to 3, 2 or 3, sometimes 3 sinusoidal modulating signals, that means all the 3, MR, MY, MB, they may exceed carrier peak in a carrier cycle. That's first point. Second point is only one phase switches. 2 phases are clamped, or pulse dropping is there in 2 phases. Only one phase switches. Then pulse dropping for more than 120 degrees in each half cycle for each phase. Okay, pulse dropping for more than 120 degrees. Then very low frequency distortion. So the distortion level will be very high here. In average pole voltages, average line voltages, and average phase voltages occurs. So level of distortion will be higher. Okay. Then trajectory, or I should say magnitude of rotating reference vector varies with time. It's not constant. Then trajectory of tip of Vref is hexagonal. Okay. Then next finding is angle of rotating reference vector Vref varies in a piecewise linear manner. In a piecewise linear fashion. You have seen angle varies like this, piecewise linear fashion, with time or with fundamental angle omega t. Right? And finally, okay, so these are this is the summary. M is very, very large. It's almost square wave mode of operation. Can I have now complete square wave mode of operation? Yes. For M greater than 3. If you go for M greater than 3, for example, we can take M equal to 3.25 or so. You will get square wave or 6-step mode of operation. 6-step mode of operation. So in that case, 3-phase average pole voltages will be like this. 3-phase average pole voltages. They will be like this now. They will be 100% square. So this is pole voltage, average pole voltage, VRO average. 0.5 minus 0.5. Okay, VYO average will be like this. This is VYO average. And so for entire period, there is no switching at all. No switching at all takes place. No phase switches. Okay. And this is VBO average. These are average pole voltages. What will be your average 3-phase average line voltages? 3-phase average line voltages will be same as that for square wave mode of operation or 6-step mode of operation, which you have already studied. 3-phase average line voltages. Your 3-phase average line voltages will be quasi square wave like this. (1.0) minus 1.0. This is your VRY average. We can draw separately VYB average. वो 120 डिग्री के बाद शुरू हो जाएगा. This is VYB average and VBR average. VBR average, that will start after another 120 degrees. This is VBR average. So these are quasi square waves. Quasi square waves. Okay. And what about 3-phase average line, phase voltages, line to neutral voltages? 3-phase average phase voltages, they will be 6-step voltages like this. This is say VRN average phase voltage VRN. Absolutely 6-step operation. We have already studied this. This is 1/3 VDC and this amplitude is 2/3 VDC. This is minus 1/3 VDC and this is minus 2/3 VDC. 6-step voltages, phase voltages. This is VRN. I can draw VYN also for you. 120 डिग्री के बाद यहाँ. This is VYN average. And VBR average after another 120 degrees, VBR average. somewhere here. So you can complete it. Something like this. Okay. So this gives 6-step mode of operation. So your inverter has now degenerated into 6-step mode of operation. Inverter average output voltage or RMS value of inverter output voltage will be maximum. It is the maximum utilization of DC bus. But your inverter is not working in PWM mode now. It was working in PWM mode up to M equal to 3. For M greater than 3, it is now operating in square wave mode of operation or 6-step mode of operation. No doubt it gives highest inverter output voltage or best utilization of DC bus, but all the strong, notorious and troublesome lower order harmonics like 5th, 7th, 11th, 13th and so on, they will be there in the inverter output voltage, and that will create a lot of problems. Okay, so what about variation of angle? Or what about variation of angle of VDEF? आपका VDEF जो है angle varies like this: 0, sector 1, sector 2, sector 3, sector 4, sector 5, sector 6. This is 360 degree. Your angle 0 to 60 degrees, 60 to 120 degrees moves like this, then it increases like this. And what type of voltages are applied? Average voltage vector applied. Average voltage vector applied. That will be clear to you with the help of space vector diagram. This is your space vector diagram. Active vector 1 with switching sequence plus minus minus. Active vector 2 with switching sequence plus plus minus. Then this is your active vector 3 with switching sequence plus minus minus plus minus. Active vector 4 minus plus plus. Active vector 5 minus minus plus. Active vector 6 plus minus plus. This is your regular hexagon. Null vector 0, null vector 7 plus plus plus. Your reference vector will be at active vector 1 for entire 60 degree interval. Okay, so I will write here active vector 1 with switching sequence plus minus minus is applied for entire 60 degree duration. Okay, 60 degree के बाद active vector 2 is applied. So there is no switching between, no null vector is applied. There is no switching between 1 and 2. 1 is applied for 60 degree. After 60 degree, 2 is applied. So similarly, active vectors 2, 3, 4, 5 and 6 are applied after each 60 degree interval, giving 6-step mode or square wave mode of operation. Okay, then after another 60 degrees, active vector 3 is applied. Then after 60 degrees, active vector 4 is applied. After 60 degrees, 5 is applied. After 60 degrees, 6 is applied. That's all. Okay, so there is no switching, no null vector is applied, no switching between 1 and 2. Okay, we are not sampling a rotating reference vector. There is no rotating reference vector. Active vector 1 is there, applied for 60 degrees. Then after 60 degrees, 60 to 120 degrees, active vector 2 is applied. Then 120 to 180 degrees, active vector 3 is applied. Then again for 60 degrees, 4 is applied. Then 5, then 6. That completes one cycle and it gives you 6-step mode of operation or square wave mode of operation of your inverter. Okay, you don't have any rotating reference vector which will trace this hexagonal path or circular path. No, nothing like that. You have active vector 1, only one there for 60 degrees. Then after 60 degrees, this goes. You have active vector 2 only. After another 60 degrees, 2 also goes. Then you have 3 and so on. So this is how a large modulation index M greater than 3, that is high over-modulation, very high over-modulation with modulation index M greater than 3, results or degenerates your 3-phase PWM voltage source inverter into 3-phase 6-step voltage source inverter. So with this, I will end my today's lecture. So we have studied the over-modulation of 3-phase voltage source inverter, in different, over-modulation ranges. First, 1 to 1.15 M greater than 1 but less than 1.15. There we have found that very low depth of over-modulation occurs and inverter output voltage increases but not very much, and level of distortion in inverter output voltages is less. And then we have increased the modulation index. We then studied over-modulation with slightly higher modulation index M equal to 1.2. We have taken the range 1.15 less than M less than 2. And we have seen that the inverter output voltage slightly increases, and we have again seen that distortion level further increases in the inverter output voltage. Then we studied for M equal to 2, and then we studied for M equal to 3. For M equal to 2, from M equal to 2 onwards, your inverter, rotating reference vector traces this hexagonal path. The tip of the rotating reference vector is it's hexagonal for M equal to 2 and as well as for M equal to 3. And we have seen the variation of angle of rotating reference vector. We have seen the variation of the magnitude of rotating reference vector, how it varies. And we have also seen that as the modulation index with over-modulation, we increase the inverter output voltage, no doubt increases. The depth of over-modulation increases, but at the cost of more and more distortion. And finally, if you make over-modulation with modulation index more than 3, greater than 3, very large this modulation index, your 3-phase PWM voltage source inverter degenerates into 3-phase square wave or 3-phase 6-step voltage source inverter, which we have studied just few moments back. So with this, I will end my today's lecture, and inshallah in our next lecture we will continue our discussions on over-modulation of a 3-phase voltage source inverter, but from space vector. We'll discuss that in space vector domain. So more information we can have from that lecture if you study the over-modulation phenomenon in the space vector domain. So I wish all the best to all of you. Thank you.